Thank you. Hello, everyone. I would first like to thank you all for attending our talk. The title of our talk is Exploiting CSP in WebKit to Break Authentication and Authorization. This is an updated version of our talk with new working POC with few caveats. Now, have you ever had an access to a zero-day bug which you could possibly use to take over accounts on any platform you want? Well, we kind of did. And today in this talk, I will talk about a bug that enabled us to take over user accounts on most of the web applications out there. But first, a little bit about us. My name is Sachin Thakuri, and I am a co-founder and security engineer at Threatnics, where I mostly do web and mobile security stuff. And I'm also a co-founder of ThreatCon, a security conference based in Nepal.
Hi, I'm Prakash. I'm also a co-founder and a security engineer at Threatnics, where I spend most of my time hacking web applications and sometimes playing with JavaScript and new browser APIs.
Before we move on deep into the presentation, here's a quick TLDR version of the talk. Long story short, today we'll discuss a vulnerability that was reported to Apple that Apple didn't consider severe enough to fix quickly, which then after waiting for a significant amount of time, we decided to exploit and earn some bounties by reporting them to bug bounty programs. The bug was in CSP implementation of WebKit, a browser engine used by Safari web browser, as well as all iOS web browsers, including Firefox and Chrome. The failure of WebKit to adhere to W3C specification when a CSP violation event is triggered leaked cross-site destination URI while redirecting from one origin to a different one. Now, combine this with common practice of implementing SSOs cross-site redirects to authenticate and authorize, we were able to steal codes / access tokens or any other secrets that were part of the leaked URI, which we could further use arbitrarily. This allowed us to carry out attacks, including but not limited to account takeovers, CSRF, and sensitive information disclosures. Moving on, now we'll discuss few technologies and concepts before moving on to the vulnerability itself. Starting with SSO. Have you ever seen these buttons where you can log in using Facebook or Google accounts on a third-party website and wondered how this works? Well, these features work through a technology known as SSO. Single sign-on, also commonly known as SSO, is a technology that provides centralized authentication service. Generally, users are asked to provide their single set of credentials, and authentication to all other applications are verified through a centralized authentication service. Its ease of use and effectiveness has made SSO widely popular among modern applications. In addition to being simple and easy to use, SSO is also considered more secure. SSO commonly works by generating an authentication token, which is then passed to other applications and services. Authentication token enables services to verify and authorize an identity, which is why securing and making sure that authentication tokens are kept safely is of utmost importance.
Sorry. Now, let's talk about CSP or continuity policy, which forms the core of our talk. I assume we all know what CSP is, but let's just revisit it very quickly. CSP or continuity policy is a set of policy or rules defining how browsers should load resources like JavaScript, CSS, or images, and whether to allow or deny execution of such. It's defined using an HTTP response header called continuity policy, like shown there in the slide, or using meta tag with some exclusions like report URI or frame ancestors. CSP has been around since 2010 and is now supported by all modern browsers. We can also see it being widely implemented in Web 2.0 apps and a lot of improvements happening over the years. Though setting the CSP header still seems to be a hard task because it depends on resources used by each particular page or site, and that's probably why there is not something as a default policy. And I think it's not that uncommon to make mistakes when implementing a continuity policy. And for that reason, we also have something called continuity policy report only header. And what it does is instead of actually executing the policy in action, it only reports violations, which makes it much easier to debug if a policy is working as intended or not without breaking your site. So when it comes to CSP, we always have what we call violation reports, because what if a user tries to load a restricted resource, right? In such cases, the browser blocks the request and dispatches a violation report. And there are currently 4 ways to catch a dispatch report: CSP's report URI directive, report to, reporting observer, and a security policy violation event. The report in general contains information on what caused the violation, like violated directive, effective policy, sample, blocked URI, and so on. The blocked URI, among others, is the URL that the user tried to load, and that could be something sensitive if it is a result of a redirect. For example, in case of OAuth, it contains code or access token, which makes it pretty much sensitive. So to avoid leaking sensitive information, W3C recommends user agents only include the URL of the original request. The image here at the bottom is from CSP 1.0 candidate recommendation from 2012. And even then, we had such cases covered. It says the violation reporting mechanism has been designed in a way to mitigate the possibilities of probing the behavior of another server. And it also explains why. That is, if violation reports contain the full blocked URL, the report might contain sensitive information contained in the redirected URI, such as session identifiers, which is exactly the case for OAuth. And as Sachin already said, it's pretty common in case of SSOs and OAuth, which we explore in our research. So if you notice, it recommends including the origin of the blocked URI, which is still an issue. And we have a long history of reports on that. This is a short history that we collected from Chromium's issues, which leaked the origin of blocked URI in one way or another using CSP. And all these reports share the same problem, that is the leakage of cross-origin redirect URL. So we'll only talk about the first one from 2013 by Igor Homakov, when CSP was still in its infancy. Well, this has been quoted directly from his blog post, where he demonstrated what we could achieve by using CSP's block URI directive. And we already went over what W3C recommends on that. And I hope everyone remembers what it said. So it says we can abuse CSP to detect if a user has authorized certain apps or clients, because all authorized apps will redirect to their homepage or somewhere else instead of login authorization page in case the application has already been authorized. For example, if you have already authorized Instagram on your Facebook, sending a request to Facebook endpoint for Instagram would redirect to Instagram instead of Facebook. And surprisingly, still works on Chrome and Safari with frames. And there appears to be multiple ways to figure out the host anyway. That's probably why it's still not fixed, but hopefully it will be fixed soon. And not just the origin, we've also found reports leaking full blocked URI in 2020 and 2021, which were very similar to ours, that we'll talk about shortly.
Now, let's discuss the root cause of the vulnerability. We can define a CSP policy in such a way that whenever a redirect happens to a domain with different origin, which is also commonly known as cross origin, a CSP violation occurs and a security policy violation event is fired. As you can see in this figure, our domain cm2.pw with described CSP policy makes a fetch request to domain1.com. Now, the response header from domain1.com contains a location header that now redirects to a domain with different origin, domain2.com. But due to our CSP policy, which we defined, the request to domain2.com is blocked and a CSP violation event is fired. Now, When a security policy violation event is fired, it uses security policy violation event interface at target with different attributes. And while setting values for these attributes, a failure by WebKit to adhere to W3C specification resulted in leaking 3x redirection location in document URI attribute. As you can see in the example, fb.com/secret here redirects to facebook.com/secret here. Then you can see the difference in values for attribute document URI set by Safari and other browsers. While other browsers who have followed specification mentioned by W3C seems to set those values of URI with values from where original fetch request was made, Safari, who failed to follow the W3C specification, set those values with final redirection URI. Now, you might be wondering how can this be exploited in SSO? As you can see in this figure here, when a user loads example.com, it first checks if the user is authenticated or not. And if the user is not authenticated, then as shown in the figure, it will send the user to auth.example.com, which is a SSO domain that provides centralized authentication. Now, after verifying the user is then redirected back to example.com with an authentication token. Now, the general common practice while implementing SSO is to use different subdomain or an entirely different domain, which then doesn't meet the criteria to be defined as same origin. So the final redirection that happens from SSO domain to the final domain, or in the case as shown in the figure, from auth.example.com to example.com will be cross origin, thus allowing an attacker to steal the final redirection URI. In today's modern application where authentication and authorizations are heavily dependent on technologies such as OAuth, SSO, and JWT, where secrets are passed through URLs, the leak of the final redirection URI made applications using these technologies almost always vulnerable.
Since this is fixed already, we'll just skip this part. But as you can see, we waited almost a year before we started exploring the vulnerability in the wild. Moving on to POC, the exploit was very simple. We set up a page with CSP as shown in the slide there. We just whitelist the domain we're sending requests to and add an event listener for a security policy violation event, then send a request. And that's pretty much it. So sending a request to an authorization endpoint issues a redirect to another domain with code or token appended to the URL, which is typically the case for OAuth or SSOs. Whereas the policy only allows loading of resources from the page itself and the domain specified. That is auth.example.com here. So as Sachin said earlier, an attempt to load resources from any other domain should violate the policy and trigger a security policy violation event. Then the document URI attribute would have the value of the actual blocked URI, and it contained the full URL, not just the origin. So this was the original POC that we reported to Apple and that we talked about in our talk at Black Hat, but we found several bypasses later on that we'll talk about later now. So we have just pushed an update to our CSP playground with the new exploit that we'll talk a little later now. This is to make it easier for everyone to experiment with the vulnerability itself. And the usage is as simple as on the screenshot. We just pass in a number of parameters, and the page then sets the appropriate CSP policy using the query parameters, and then it presents a button to proceed further, which is required to open a pop-up. And then clicking the button would then submit the form and send a request to the URL specified, and then that will trigger the CSP violation event, which will contain the redirected URL, which in this case, which in real life would contain the URL with code or a token. So the source code is also on GitHub, and so feel free to use as you please.
So now we have a short demo. In this demo, we'll demonstrate how we were able to take over Instagram accounts using Facebook's OAuth, and that we also reported to Facebook. So the attacker will first get the OAuth endpoint for the target application. That would be the location where the OAuth is hosted. And please make a note that the attacker will also generate a nonce or a state value that will be used in this attack. And then the attacker will craft that URL into the POC URL that Prakash just explained about. And then this particular URL will be sent to the victim. And this is the victim's browser where you would open up the attacker control domain. As you can see, the victims need to be signed in, obviously, for the account takeover issue. And as you can see, a pop-up opens up with Facebook access tokens, which will then enable an attacker to log into Instagram. And this is a one-click account takeover POC. We also had zero-click account takeover POCs on previous version. And we also have one similar to that that Prakash will discuss later. So yeah, now the attacker is logged in as a victim. So this is how we demonstrated an Instagram account takeover using Facebook OAuth and the bug that was ignored by Apple for a very long time. Okay, now let's discuss impact. It took us a while to understand the full impact the vulnerability had. The vulnerability did not just affect Safari browser, but because of the Apple's App Store policies that states that apps on iOS devices that browse the web must use the iOS WebKit framework and WebKit JavaScript, which means that web browsers can't implement their own rendering engines. They must embed a version of Safari's rendering engine, which then made browsers like Firefox, Chrome, Opera in iOS devices vulnerable. And due to the nature of design of OAuth, where almost every implementation of OAuth that exists were vulnerable. Using the bug, we could take over Facebook, Instagram, and WhatsApp accounts. The bug also affected Google's SSO, which means Google products using Google accounts, central authentication were also vulnerable. Cryptocurrency platforms, social networking platform, e-commerce platform, and more. In today's modern application, it's very rare to find an application not using OAuth. So let's just say the numbers were very high. And since the vulnerability affected SSO, so it's obvious that different SSO providers were also affected by this. And nowadays, many applications make use of login with third-party features, such as login with Facebook or Google to provide the user with easy and seamless authentication experience. And since most of these features make use of OAuth, these applications implementing login with feature were also affected, thus allowing an attacker to take over accounts and platform implementing these features. For example, let's say you have an e-commerce website where you have a feature that allows users to log in with Facebook account. Then an attacker could basically take over accounts of your users in your e-commerce website by stealing Facebook OAuth tokens. Moving on, let's discuss some roadblocks and general misunderstanding that we saw among security teams of different bug bounty programs that we reported to. Let's start with ITP, or Intelligent Tracking Prevention, which is a privacy feature developed and implemented by WebKit and has been in use since October 2017. ITP uses machine learning model to detect cross-site tracking capabilities and aims to reduce them by taking different actions such as full third-party cookie blocking, reducing the accessibility and longevity of first-party tokens and cookies, first-party cookies, and then local storage capping and deletion, downgrading third-party referrers, and more. And due to the nature of the attack, where the bug relied on making third-party requests, ITP rendered the attack unusable on latest version of WebKit. And according to documentation from WebKit, to circumvent it, there needs to be a user interaction. It could either be a tap, a click, or a use of the keyboard with your website as first party. So in a real attack scenario, what we did was we opened up a tab using window.open, and then we kept polling the vulnerable endpoint until the user interacts with it. And much later, we discovered another workaround where we found a way to make the exploit work without triggering the ITP by using from action attribute, which Prakash will discuss more about. And when we started submitting this vulnerability to several bug bounty programs, we noticed that a few of them had several misunderstandings around them. So we'll discuss a little bit about that as well. And one of the common misunderstanding among security teams of several programs was around authorization code. Unaware about its capabilities and how sensitive it is. The misunderstanding was that without the ability to exchange authorization code for access tokens, the authorization code were useless since exchanging them required application ID and application secret. While the statement above is true, in a case where OAuth was used for authentication, simply having an access to authentication code was enough to get access to victim's account. Making a request to an authorization endpoint with stolen authorization code with attacker generated state or nonce value would allow an attacker to authenticate into victim's account. And another common misunderstanding was with regards to state or nonce value and its capabilities to prevent attacks in OAuth. While using state in OAuth is an excellent way to prevent CSRF attacks and to redirect users to where they were before the authentication process started, apart from that, the state really doesn't provide any additional security features. And even if the state value is bind to a token, an attacker can always generate a fresh state value, which then can be attached to an OAuth endpoint URL to send to the victim. The resulting token of that particular request then can be used by an attacker without any issue. And the same thing was also demonstrated in our demo above, where we saw that nonce value that was implemented in Facebook and the state value did nothing to prevent the attack. Now, so these are some stats based on bug bounty programs and reports we made. In total, we were able to harvest more than $100K in bounties. And the response from the bug bounty programs were kind of mixed. While some programs took the issue very seriously and applied a fix in under 21 hours, which was really impressive, some took months to just understand the vulnerability. And some of the programs also relied on WebKit to come up with a fix. While some programs like Dropbox and Polonix took it one step further by using their contacts at Apple and asking them to come up with a fix. The highest single reward was given by Coinbase, which was also the fastest program to fix the issue. And Apple took more than a year, a total of 457 days to come up with a fix. And in the end decided that the bug does not qualify to be awarded a bounty because it does not meet the Apple's published bounty categories. And ironically, while this bug in WebKit made so many applications in the internet vulnerable, the Apple's implementation of SSO and OAuth were not vulnerable.
We saw how we can exploit the vulnerability and how severe it could be. Now let's discuss some fixes as well. As a developer or site owner, we can use any or a combination of these methods to prevent such vulnerabilities altogether. They're all very easy to understand and implement as well. The first one is to use post method instead of get, which actually aligns with the practice of never sending any sensitive information over the URL. For example, SAML or Security Assertion Markup Language already uses post instead of get for transferring tokens. And the second one is to use post methods for cross-domain communication. These two fixes actually are already available by OAuth for OAuth or OpenID Connect, as can be seen on the image on the right. They could be specified via response underscore mode parameter as long as the authorization server supports them. However, it's still necessary to disable or remove the support for query and fragment modes, which is again the 302 server-side redirect modes. While same-side cookies help prevent almost all cross-site attacks, it appears it doesn't help in this case. So not if the cookies are same-side lax. So we have removed it from our list of recommended approach. Because a security researcher named Julian, or Jubops, his Randall, disclosed that it was possible to bypass same-side lax cookies with CSP's form action. And with a little bit of fuzzing, we are able to get it to work in Safari as well. In short, what we do is submit a form with methods set to GET, which, as you may have guessed, is a simple navigational request. So if the URL is not specified explicitly in CSP's form action, it triggers a violation. So while we did mention it as one possible approach in our previous talk, we have removed it now because it doesn't really prevent this particular instance of cross-site attack. Similarly, we have PKCE for OAuth, which makes the exploit kind of useless because we also need code verifier to make use of the leaked code. The other one is to ask for authorization every single time, also supported by OpenID using the prompt parameter. Apple did the exact same, and many others too. One can also use client-side redirects instead of 301 or 302 in combination with XFrame options or CSS frame ancestors. Twitter, for example, uses this method for redirect, and many programs we reported the vulnerability to also fix the issue using this approach. The last one is to validate the referrer or origin against the client, though we do not recommend using this approach as it suffers from the same issues as with CSR protection with referrer or origin. There's also something called resource isolation policy, which uses face metadata, but Safari unfortunately doesn't yet support them. So it's still not the best approach yet. So browsers also have some mitigations in place to avoid such leaks besides same origin policy. However, the strategies listed here are specific to CSP. We also found something that these strategies did not cover. So let's briefly go over them anyway. The violation report now include the URL of the original request, meaning we only get what we already know. Furthermore, browsers ignore the path component of a source expression if the resource being loaded is the result of a redirect. This is to prevent leaking of path information, which was demonstrated in Homakov's post. The spec also gives an example for easier understanding, but we'll leave it at that. So after our reports, many programs, including Facebook and Coinbase, came up with their own fixes. Their fixes revolve around checking if the user agent is of Safari, and only if it is, they would use a different approach. And for all other user agents, their workflow remained the same. So it seemed a simple change of user agent would bypass the fix. And an obvious place to try it was iPhone or iPad, since all browsers on iOS devices must use WebKit as the engine. And they're all actually same. So just using Chrome didn't, but just using Chrome didn't work. And changing to desktop side did. So we found a bypass, but it appeared that the change of user agent wasn't inherited in subsequent fetch requests. So we tried all requests from a project called HTTP Leaks by Cure53, which lists all possible ways to send an HTTP request to an external URL using HTML tags, and we found that a ping or anchor tag with ping attribute did the work, which actually inherited the user agent that we changed to desktop site. So we had found it another bypass, but during our hunt for bypasses, we noticed something peculiar. After some digging, we realized that we had already found another 0-day. This time it wasn't CSP, but it was cross-origin resource sharing that actually I briefly talked about in the browser mitigation. So the finding was as easy as shown here. We just needed to add a catch handler to the fetch request, and it disclosed the destination URL. So we set our plan to disclose the vulnerability with Apple, and surprisingly, it got fixed right before our talk at Black Hat without us being notified. And it turns out that other researchers had also found the same vulnerability. Our research paper was released a few months back on cross-site leaks or access leaks with some excellent examples, which also included this. They've done an awesome work listing all possible cross-site leaks, which also included this as one of their POC, one of their test cases. So I think it was fixed because of their report instead of ours, but the original reporter was us. So this one is also fixed. However, the story still continues, and surprisingly, it still works in latest version of Safari, which is 15.4. And we identified yet another bug that's exactly the same as the one we already talked about. And the only change here is the change of HTTP header called confidentiality policy report only. Here we are using report only header instead of confidentiality policy. And instead of document URI, it's now blocked URI. So those are the only changes that required it to work again. And it still works in latest version of Safari, but it only works in iOS for some unknown reason. So the continued research gave us the opportunity to come up with new bypasses and workarounds for roadblocks that we talked about. So it no longer requires a click, and the redirect does not have to be across origin either. So now the three key things to take away are always revisit your bug. In our case, we found similar bugs with same impact in 3 different instances, and that allowed us to bypass different roadblocks that we previously had. For example, same-site cookie bypasses and cross-origin redirect. And because browsers do not always follow this spec completely, use defense in depth to mitigate browser flaws whenever possible, instead of entirely relying on browsers. And with that, we are at the end of our presentation. Thank you for listening, and we are open to your questions.